We start today on page 13. If you guys could head to page 13, that would be great. So I wanted to answer just one homework question from a previous homework. Remember the question about the dentists in New York City? This was one where you were just, again, just kind of like, it's not a guess, it was an estimate based on lots of sort of little guesses. But in case you're curious about what the like quote unquote right answer is, and remember to be a success for this kind of a question, what do you need to get right? The same number of digits is the answer. Okay, so roughly in New York City, there are between 4,000 and 5,000 dentists. So if you had something in the thousands, then you win. If you had something where you were in the 10,000s, you're a little too big. Something in the hundreds, a little too small. Okay. So we are on page 13. We'll take just a quick peek at the calendar. Remember again that you have a copy of this on the back of your syllabus. Today we cover working with large numbers. I will say that the first 4 classes, including this one, in my mind, are all about numerical literacy. We talked about the penny solving, the penny filling problem, orders of magnitude like this dentist question, percentages, and then finally today lots of stuff about really big numbers. I think the common thread for those 4 classes is numerical literacy. And then starting when we come back on Tuesday after the weekend, we begin a completely new topic, and it's going to be kind of a major topic for us. We'll talk about voting for the 4 classes that follow this one. And what happens after those 4 classes? We have our test. We have a full period review day, and then we have our test, okay? So at the end of today, we're halfway through the material for the first test. All right, let's go ahead and take a look at page 13, and we will start here with number 1. And can we get Mary to read number 1? Okay, we have a lot of blanks for you guys to fill in. 10 to the 3rd, we actually saw that on the very first class, is 10 times 10 times 10, which is 1,000. And how do I know how many zeros to put after the 1? You know, put the 3. That's real nice, easy shortcut for 10 to a power. You just put that many zeros, whatever the power is, and we know the name of that number quite well. It's 1,000. I would like you guys, with the help of the people around you, to fill in the rest of these blanks. It's not going to be too hard to get the number of zeros right, but some of the names will become a little bit fuzzy as we get really big. Go ahead. 10 to the 6th, it's a 1 followed by 6 zeros. What's the name of this number? Right, so this is 1,000,000. 10 to the 9th, 9 zeros. What's the name of that number? It's 1 billion. And then they start, like things start to break down for us as the numbers get just so huge. 10 to the 12th is a trillion. And you might feel like, well, you know, like where in my like daily life will I ever have a number that's as large as a trillion? Well, the U.S. national deficit is in the trillions. 10 to the 15th, quadrillion, good. And if you're paying attention to prefixes, you actually might be able to kind of figure out the names of these things. All right, million, I don't know what's going on there, but bi is a prefix which means 2. Tri is a prefix which means 3. Quad is a prefix which means 4. So there is a pattern happening here. And in fact, the very last one is the prefix that means 5. Anybody know it? It's quintillion. There are some musical groups that are known as quintets. They have 5 members in them. There are some women who have quintuplets, 5 babies at one time. Bless their hearts. Okay, let's go down to number 2. Grace, can you read number 2? Okay, so then we got some numbers and then what these numbers represent. So first of all, just think to yourself, what is the name of that number? Is it trillions? Is it billions? What is that? That's a million. So a little over a million. Approximate number of times Taylor Swift's song was played on the radio in 2010. That made her the most played artist on the radio. She was also the most frequently played artist in 2009. Again, think to yourself, but don't say it out loud just yet. That 300, what is the name of that number? Okay, now let's say it out loud. That's 300 million, and we've talked about that's about the US population. It is also about how many pennies we could squeeze into this room. Okay, very carefully think about that next number with the 12. You've got the names up above. And that number is called? That's trillions. That's 12 trillion. The national debt. Actually, I probably should update this because I haven't updated it in a little bit. So it's certainly higher than this right now. But presumably it's still got the same number of digits, I hope. Okay, next page. All right. You actually do have the name of this number on the previous page. So find it. And let's see if we can figure out what to call that number. What is the name of this number? Those are quintillions. Quintillions. If you count the number of trios of zeros, 1, 2, 3, 4, 5, 6 trios, 18 zeros. That's quintillion. 43 quintillion is the number of different positions of the Rubik's Cube. You guys remember this puzzle, right? How many of those positions are what we call solved? One. There's one way to get the Rubik's Cube to be solved. The rest of the 43 quintillion, it will look mixed up. But that's how many ways there are to mix up the Rubik's Cube. Okay, this one, I don't even think we have the name for this thing on the previous page. It's Avogadro's number. Any chemists, do you recognize this? Like maybe we've seen this number in some chemistry class. It's the number of hydrogen atoms in a gram of hydrogen. So a gram of hydrogen, not very big, but atoms are like super tiny, so you can squeeze a lot of them into a gram of hydrogen. You can see that these numbers they're kind of getting hard to read, actually. Even though we've got commas separating every 3 digits, it's still tough to process that number. And this is where scientific notation comes in. So we're gonna spend a little bit of time rewriting these things in scientific notation because it's just not very useful to write it out with all these zeros. It's hard to write, it's hard to read, lots of chances for either person to make a mistake, the writer or the reader. Okay, and then we also have this number, point, and then lots of zeros with a 2, so very, very close to 0, that number. And that's about how many seconds it takes for a modern desktop computer to perform one floating point operation. So just to do one little calculation like 8 times 5. It takes about that many seconds, which is a tiny, tiny, tiny little fraction of a second. So maybe it's not so surprising that you can give it like a huge calculation to do and it'll appear to do it in no time. Well, it's because it can do every little addition, subtraction, multiplication, and division in that tiny, tiny sliver of a second. Okay, let's go to 3. Gina? Okay, so first thing we need to do is understand how to translate a number like 230 into something times 10 to the something. All right, let's take a look at there's a pattern we're looking for here. 230 is equal to 230 times 1, agree? And maybe something that is not as familiar to us, 10 to the 0, what is that really equal to? It's not 0. It's a good guess. 10 to the 0 is 1. This might be something we remember from our previous algebra class. Any number to the 0 power is 1. It's weird, it's counterintuitive, but it's still a fact. Any number to the 0 is 1. Okay, let's look at the next line. Still have 230. Would you agree 230 is really 23.0 times 10? Yes? And then 10 is really 10 to the first. So those two guys are equal. And then the next line, back to 230, it's 2.30 times 100. Do we buy that? So 2.30, if you multiply a number times 100, the effect is you take the decimal point and move it 2 places to the right. So 2.30, if you move that decimal place 2 to the right, you get 230, which is just what we wanted. And 100, we've already seen, is 10 squared. And so the basic idea here is how do you convert 230 into something that we're about to call scientific notation? You just have to understand what effect moving the decimal point has on that power of 10. So let's go to Lucas. Right above number 4, as, yeah. Okay, so there's two things going on here. First sentence that Lucas read is that if you want to move the decimal point to the left, you need to increase the power of 10. Every time you move the decimal point to the left, you increase the power of 10. The other thing going on here is how do you know when to stop? I've got 230 times 10 to the 0. That is equal to 230. Also, 23.0 times 10 to the first is equal to 230. And then finally, 2.30 times 10 squared. They're all equal to 230. But only one of them is scientific notation. And this is the second thing that Lucas read. He said the number in front of the 10 needs to be between 1 and 10. Is this number right here between 1 and 10? No. Is this number right here between 1 and 10? No. Is this number between 1 and 10? Yes, that one is scientific notation. So this thing right here needs to be between 1 and 10. So this whole number is in scientific notation. The last one. If I want scientific notation, this is the only way to write it. For 230, that's the way to write it with scientific notation. You need to break it down to a decimal, but not just any decimal. 23.0 is no good. You got to make it so that you keep going until that decimal point lands in just the right spot, which is 2.30 in this case. Yeah, so let's write down actually one more. Maybe we should have written this. 230 is really 0.230 times 1,000. The decimal place 1 to the left, increase the power of 10. 0.230 times 10 to the third. It's the same pattern that we had up above. So 0.230 times 10 cubed, that's another way to write the number 230. Is that in scientific notation? The answer is no, because 0.230 is not between 1 and 10. So you got to go just to the magic spot and don't go too far. Okay, so another way to say that, and this might be something that some of you have seen, is that the number in front of the 10 has one digit to the left of the decimal point. If I look at this decimal point right here, how many digits are there to the left? 2. That's no good. If I look at this decimal point, how many digits are to the left? There's nothing out there. If I look at that decimal point, how many digits are to the left? 1. That's the goal. You always want one digit to the left. Okay, so let's give this one a shot. Number 4, write 8600 in scientific notation. Currently, the decimal point is right there. I need to move that decimal point to the left. If I move it here, is that good? No. If we move it to between the 6 and the 0, is that good? If I move it between the 8 and the 6, is that good? Yes, that's where it goes. So I know right away it's going to be 8.6. I'll write the other zeros, although they don't matter. But it has to be 8.6. Yes. That's what's going to be on the 10. So how many places did that decimal point move? 3. 8.6 times 10 cubed. That's scientific notation. Questions on that one? Okay, so some of you guys, I think, have seen scientific notation before today, and that's great. Some people think that scientific notation means whatever number is up on the power, that's how many zeros there are. How many zeros are there in 8600? There are 2. Is that the right power? No. Number of zeros is not right. It's not always right. So don't think of it as how many zeros. Think of it as moving the decimal point. How many times do you need to move that decimal point? That's always going to be the right power. Okay, let's try number 5 here. Haley? Okay, so starting at the bottom of the previous page, starting with that 300 million, I want you to write each of those numbers in scientific notation. Don't do the computer one. We'll do that one last. But do all the other ones in scientific notation and check with your neighbors. Okay, how are we doing with scientific notation? Loving it. First one right, 3 times 10 to the 8th. You don't need to put the 0 after. You could just put 3. Yeah. Yeah, so the first one, oh, I forgot the Taylor Swift one. Okay, so the Taylor Swift one, 1.128. Again, looking for one digit to the left of the decimal point. And then we just have to count, not the number of zeros, but how many spaces we moved. So that's times 10 to the 6th. Okay, so can you guys check my work? Did I get these 3 right? Okay, any questions on those 3? All right, let's move on to the ones on the next page. Okay, this is 4.313. Okay. All right, so this is 4.3 times 10 to the, is it 19? Okay. 6.022 times 10 to the 1, 2, 3, 4, 5, 6, 7. 7 times 3 is 21, and then another 2. 23? Is that right? So back when I took a chemistry class, this was the version of Avogadro's number that I was taught to memorize. It was 6.02 times 10 to the 23rd. And I still have that somewhere in my brain. I don't really know what it means, but it's there. So 6.02 times 10 to the 23rd. And, you know, again, the whole idea behind scientific notation, number 1, it's easier to write down. Number 2, it's easier to read. Number 3, it's something that's standard in the scientific community. So whether you're writing a paper here in English, or you're writing a paper in Spanish, or in French, or in Russian, the numbers, we're all going to look the same. And this is something that the scientific community has just agreed on, so we're all speaking the same language, at least in terms of the numbers. Okay, let's come back down here to number 6. We are in the back. We'll go to Morgan. Okay, so here's the idea. Again, yeah, this is kind of going backwards. So we're moving the decimal point. Where does it need to go to? It's got to go between the 4 and the 6. So we're going there, 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 and there, because you want one number to the left of the decimal point. So it's definitely 4.6 times 10 to the, yeah, so how many? Was it 5? 1, 2, yeah, 10 to the negative 5. That's it. So if you go the opposite direction, if you go the quote wrong way, it's just a negative, that's all. So it's the same pattern, but backwards. Are there questions on that one? So you count how many places you move, not how many zeros. There's 4 zeros there. It's not negative 4. It's how many moves. Okay, go back up to this calculator, or the computer number, this one with the zeros and the 2. Let's write that one in scientific notation and check with your neighbors. Okay, how many movements? I heard 1 vote for negative 10. Is that right? Okay, that's good. Move that decimal point. So there's 1 digit to the left of the decimal point. You don't have to write 2.0, you can just write 2. I put it there just so we really see that the decimal point is somewhere. Yeah. Okay. Any questions on scientific notation? All right, so the good news is, now that we're experts in scientific notation, you could read any science paper you want to. It's wonderful, right? Just open the door. Yeah, it's great. Okay, let's go to number 8 and see what the calculator does with all this. Alex. 8. Good. So your calculator doesn't generally write lots of zeros at the end. It writes it in scientific notation as a default. So if your calculator says 4.1E8, please don't write that on a test answer, because E is calculator speak. It is not human speak. Humans write things in scientific notation. So it's your job to be able to translate the calculator language. That E always means the exponent of the 10. E for exponent. So if you see 4.1E8, it means 4.1 times 10 to the 8th. You can write that, or you could write it out a long way. Now, if you have a calculator on you right now, let's take it out and see if we can figure this out. So I'm going to do this on a couple of different calculators, and if yours looks different from either of these, that's okay. So you know the most annoying thing about my virtual graphing calculator here is that it powers off after 5 minutes, just like the real one, which seems quite silly to me. Okay, so let's go over here first. So what I'm going to do is type 4.1 and then E8. So can somebody find, is there an E button here? Actually, I don't have an E button here. I have a 10 to the X button. All right, forget that guy. Let's go over to this one. Is there an EE button on? Yeah, let's use the right-hand one. So we're looking for something like this, 4.1, and then it might be hard to see for you guys in the back, but in yellow, there's something that says EE on this calculator. It's right above the comma. Now you might have to hunt around for a button on your own calculator that says E or EE, but I'm going to hit second and then E, and you see it, it says E. And then we were looking for, it was 4.1 E8. So if I just hit 8 right now, it's going to say, oh, I know what you mean. You mean that number with lots of zeros, 410 million. .1 times 10, and then up arrow is the power button, 8, absolutely. So they both say the same thing. Why do we have the E stuff? Well, it's just a little bit quicker to write it that way. Okay, so we'll just walk around real quick and make sure we can find this. Okay, so let's come back together. And I will say, I think it's a whole lot more reliable to use that E button than to type in 7 or 8 zeros. I think it's easy to make a mistake when you are repeatedly hitting zeros. It's hard to even count them when they're on the screen. So take advantage of that E button. It just means times 10 to the. Okay, we'll go to number 9. Gary. Okay, so this is true. I found this in, I think it was in a Reader's Digest. 6.25 billion hot dogs over the course of the summer. And that sounds like a lot of hot dogs, but it's like 6.25 billion is just such a ridiculously large number. I can't even comprehend it. So what I want to do is break that number down. Let's get it so that we've got something more manageable. Perhaps how many hot dogs per second? Like maybe if that number is small enough, I can visualize, I can say, okay, I understand now, number of hot dogs per second. So maybe in some previous math class, you guys have been doing like unit conversion stuff, but we'll start here. 6.25 billion, which means times 10 to the something. So yeah, what's the right number for billion? Is it 12? One vote for 9. A few more votes for 9. Okay. So billion is 10 to the 9. Now that's 6.25 billion hot dogs over the course of the summer. So it didn't say specifically from this date to this date, but could we agree like how many months are there generally in the summer? Is it 3? I mean, like I feel like, is it 2.5? But we have 12 months total, right? And how many seasons? 4. And I think that they're all equal, you know, like close enough. So let's call summer 3 months. You know, like June, July, August, even if you might still be in school in part of June or something. So so let's say that 6.25 times 10 to the 9th, that's HD for hot dogs, and then that's over the course of 3 months. We buy it? Okay, but what I need to do now is break this thing down to seconds. I can't deal with months because it's just too many hot dogs for me to think about. So we're going to multiply by a fraction. And I'll give you one of the like basic premises of algebra. Like there's just a couple of fundamental things for algebra and then lots of other details. One of the basic things for algebra is that the only number you can multiply something by without changing it is what? Is 1. The only number you can multiply by without changing the number is 1. If you take 7 and you multiply by 4, it's not 7 anymore. But if you take 7 and multiply by 1, it's still 7. I need the answer to still be 6.25 billion hot dogs over the course of the 3 summer months. I can't change it. I can't just multiply by 7, but I can multiply by 1. So what we're going to do is we're going to make a fraction here, which is really 1. Now, if I'm telling you a fraction is 1, what can you tell me about the top and bottom of that fraction? They're the same. Yes? If you have like 5 over 5, how much is it? It's 1. That's the only way to make a fraction 1. Top and bottom are the same. So here's what we're going to do. I have months on the bottom. I'm not thrilled with that. I'm going to put months here. Give me a smaller unit of time that goes into a month. Is days, right? So the conversion we're about to put in here, okay, let's see. 1 month, roughly how many days are in the average month? About 30. If we believe that 1 month is the same as 30 days, then the top and the bottom of this fraction are the same, which means the fraction is really equal to what number? It's really equal to 1. So it's perfectly okay to multiply by that. I haven't changed anything. But what I have done, if I cancel the months, is I now have hot dogs per day. That's good. That's closer to hot dogs per second. Let's see if we can multiply by another fraction. What's the next word that I want to cancel? I'm going to put it up here on the top. I've got days on the bottom. I don't want that. And then the next unit of time that days are comprised of is hours. So can you guys figure out, I'll put the 1 day, and then you got to put something on the bottom that is equal to 1 day. So it's 24 hours. So there's another fraction which is perfectly good because it's just a fancy form of the number 1. And then what happens here in terms of canceling? Cancel days. And now I can do the calculation on the calculator, but I've got hot dogs per hour. Getting there. There are 2 more fractions I want you guys to multiply by. Talk to your neighbors, see if you can figure out what those fractions are. Again, the goal is hot dogs per second. Okay, let's come back together and then we'll use the calculator to get the actual final number. What are we putting here for hours and minutes? How many hours? 1. And how many minutes? 60. And then the good thing is what cancels? Now we can cancel hours. And then finally, minutes and seconds. How many minutes? 1 minute if we're doing minutes and seconds. And how many seconds in a minute? 60. And then, again, good cancellation happens. Minutes cancels. So if we just look at the units, what's the only unit left over on top? There's lots of 1s, but what's the unit? Yeah, that's the number. It's hot dogs. Hot dogs is the only unit left over on top, right? What's the unit left on the bottom? Seconds. So when I type all this into my calculator, it's going to give me hot dogs per second, and that was the goal, okay? All right, so it is important for me to be able to type it in. I think typing it in is going to be pretty easy, so I just want to pause. Are there any questions on coming up with these fractions? Because on the test, I'm going to ask you to come up with fractions like that. So is it clear, like, how to come up with them? Any questions on that? What's that? Okay, so let's type this thing in. And I'll say there's really only one basic mistake you could make when you're typing something like this in. Let's clear that. Okay, so the only basic mistake, it's going to be hard for me to put this somewhere. The only basic mistake you can make, all right, so I'm going to do this, 6.25. And then instead of times 10 to the 9th, I could do E. You don't need to do that. You could just type times 10 to the 9th, but we'll be fancy. E9. Okay, what are all of the things up on the top? All of the numerators of the other fractions. They're all 1. So you could do times 1, times 1, times 1, times 1. I'm not going to type any of that. I'm just going to look at the bottom. So what's the next key I hit to say we're on the bottom? We're dividing. Okay, this is the moment right here where we could make the mistake. If you say divide by, okay, on the bottom I have 3 times 30 times, and then lots of things, right? I've made a mistake, a fundamental mistake. Yeah, we need parentheses. I need to tell the calculator all of those things are on the bottom. And you tell the calculator all the things are on the bottom by putting parentheses around all of them. So all of the things on the bottom are going to be in the parentheses. 3 times 30 times 24 times 60 times 60. This is going to be my answer. So how many hot dogs did we consume per second? Oh man, what did we do wrong? Extra one. Okay. 800, about 800, 800, we'll just say 800. So what does it mean? 800 hot dogs per second consumed over the summer. Yeah, that's pretty nasty if I'm being honest. All right, what's that? I would probably, yeah, you could say 804. On the test, it's my job to tell you where to round it. So I'll always be really explicit. Yeah. All right. So that's our answer there, about 804. Any questions on how to type that in? To tell the calculator everything is in the bottom. Yeah. Okay. Everybody's able to get 804 on their calculator? Okay. So let's move on to the next page. Everybody has what they need from this? Oh, somebody, remember I had said on Moodle, you'll find a PDF of the class notes with all the color and writing up here. And somebody had said that they weren't able to see it. And I said, no, it's up there. I posted it, you know, like on Friday of last week, and I did. But yesterday I learned that the default when I post something on our Moodle page is to make it hidden to the students. So that's why you couldn't see it. So anyway, I unhid everything yesterday, so it is there, and we won't have that problem again. So anyway, you should be able to access a copy of this. I will update it at the end of every week, so you'll always have an updated copy if you want to grab that PDF, okay? All right, next page. Okay, so we've been talking about large numbers. We had Taylor Swift, we had the Rubik's Cube, we had Avogadro's number, we had hot dogs that we consumed over the course of the summer. Lots and lots and lots of large numbers. Another place that large numbers appear very naturally is in astronomy. If you think about the universe, things are spaced out so ridiculously far that it's hard to even have a concept of how far apart these things are. So what do we do when things are just too big to imagine, too big to visualize? Well, sometimes you build a scale model. And maybe you've seen a scale model of a train, right? Really, really tiny train set, but it's a scale model, which means that everything in your little tiny train set is supposed to be the right ratio. Like it's not the same size as the actual big train, but if, for example, the engine of the big train is twice as long as the caboose, well, then when you scale it down to your little model, the engine of your little scale thing will be twice as long as the caboose. Yeah, Melissa. Yeah, they're in proportion. Yeah, so supposedly every little detail is kept exactly in the same proportion. That's good. So we're going to do the same thing here. We're going to think about a scale model of some of these stars here in our solar system and beyond. So let's get somebody to read this first part. I think we're up to Greg. Yes. Okay, so taking a look at this table, we have, according to what Greg just read, these are the 8 brightest stars when viewed from Earth. Okay, so clearly the sun is going to be the brightest star in our sky. In fact, it dwarfs any other star that you might see if you're out there at night because it's so close to us. I think the sun is a modest size star. I don't think it's particularly big relative to most stars. I don't think it's particularly small. I think it's just an average size star, but it looks so huge in the sky and it is so bright to us because we are basically next door neighbors with it compared to the next star that we could see, which is Alpha Centauri A. And so we've got a bunch of these stars here. Maybe some of these names you've heard of. Rigel is a sort of a common name out there. And the distances for these stars are so enormous that like miles is not going to do it justice. If you wanted to talk about how many miles away a star was, you'd be writing forever because the numbers would be so huge. So we introduce a new unit of length, and it is called the light year. Now, if I say light year and I ask you what is it measuring, well, I hear the word year and I imagine it's measuring what kind of a thing? Time, right? Years measure time. light year does not measure time. A light year is a distance, just like a meter or a foot or a mile, okay? A light year is a distance. What is it? It's the distance light travels in a year. Light year is the distance light travels in a year. It's not a time, it's how far. How far a beam of light goes if you let it go for a year. Okay, now it turns out light is really freaking fast. So a light year is a really, really long distance, okay? Greg read for us that a light year is about this many kilometers. Now, I know that we are one of, I believe, 3 countries that don't use the metric system. And so this idea of doing things in kilometers is going to be quite uncomfortable for most of us. So I'm actually going to change it. I think it's quite silly that we are not using kilometers here in this country, but we'll go ahead and get to be something more familiar to us. Could you guys replace that number with 5.88 times 10 to the 12th miles? Okay, so here's my little 30-second soapbox about why we should convert to the metric system. Kilo means what number? 1,000. So if I wanted to know how many meters were in a kilometer, it's 1,000. If I wanted to know how many liters were in a kiloliter, it's 1,000. You guys have seen centimeters. Centi means what? 100. 100 centimeters in 1 meter. How many inches in a foot? 12, of course. 12, right. How many feet in a yard? 3, yeah, it's no nicer number than 3. So we're choosing how many feet in a mile? 5,280. Raise your hand if you have that number in your brain. 5,280. Yeah, that's how many feet in a mile. Right. So look, the choices that we are making, 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile, instead of the choices in the metric system, which are 10 and 100 and 1,000. It's even silly what we do with temperature. What's our unit of temperature here? Fahrenheit. Fahrenheit is dumb. What's the freezing point of water in Fahrenheit? At what temperature is 32 degrees? Raise your hand if you have that stupid number in your mind. 32 degrees. Boiling point of water in Fahrenheit? 212 degrees. Raise your hand if 212 is in your brain instead of other useful things. What's the freezing point of water in Celsius? 0. What's the boiling point of water in Celsius? 100. We choose 32 and 212 Fahrenheit instead of 0 and 100 Celsius. Okay. All right. So let's see if we can handle some of this. Let's go to. We're going to do the first couple of these together. Oh, one more change. We've changed kilometers to miles. So just update that. All right, so here's what we're going to do. Let's focus on Alpha Centauri A, which is 4.4 light years away from Earth. So presumably this is a pretty bright star in our sky. If it's night out and it's not cloudy and you don't have a lot of lights of the city around you, should be able to get a pretty good look at Alpha Centauri A. Now this is kind of weird for some people to think about, but the light that you see coming from Alpha Centauri A, when did that light get emitted from Alpha Centauri A? Is it right now? The light that you see, if you look up there, you see this star in the sky. Are you seeing that star right now? What are you seeing? You're seeing that star 4.4 years ago. Because that's how long it took for the light that you are seeing right now to get to Earth. It was sent 4.4 years ago. It finally gets here, and that's what we see. And even the sun, which is really, really close relative to the other stars. Do you know how long it takes for light to get from the sun to us? It's about 8 minutes. It takes about 8 minutes for light from the sun to get to us. Suppose that this would be really bad for us, but suppose that the sun just blinked out of existence right at this moment. If we go outside, would it just be night? What would we see? We would see the sun. It would look exactly the same. When would it be night? In 8 minutes. It's really weird. Like we think everything we see is in real time. It's in the present, right? It's not. You're seeing the sun 8 minutes ago. You're seeing the stars 4.5 years ago. I know. But actually, Nicole, I'm not seeing you in the present time either. Is this an instantaneous? It takes a little bit of time for the light from Nicole to reach my eyes, right? So I'm seeing her slightly in the past, but light is so quick that it hardly matters, right? For these distances, it's instantaneous that we see each other. Morgan, Morgan, yes. Yeah, I don't know if you guys have read any like sci-fi or time traveling stuff. Right. And so like actually astronauts that spend a lot of time out there in space traveling really, really quickly age a little bit less than we do here on Earth. Yeah, thanks for mentioning that. They age a little bit less. So if you wanna hold on to your youth, just go to space. All right. Okay. So here's what we're gonna do. Here's what we're gonna do. We're gonna try to create a scale model of these 8 stars, okay? A scale model of these stars. We're gonna put Earth like right here in this classroom, and then we're just gonna line up all the other stars in a line, and we'll see how far away it goes, okay? So really, really scrunched down model of the universe. So what we're gonna do is we have to decide how much we're gonna scrunch it down. Do I wanna take the actual distances and cut them in half? No, they'll still be way too big. Do I want to take the actual distances and divide them by 100? No, they'll still be way too big. But do you get the idea here that we need to take the actual distances and divide them all by something so that we can scrunch it down to size, something we can visualize here in our classroom. So here's what we're going to do. For this particular problem, the scale ratio, that's a phrase we have not defined, but it means how much are you scrunching down by? How much are you dividing by? The scale ratio for all of the stuff we're going to do in this activity is 1 to 1 quadrillion, which is 10 to the 15. We saw that number earlier today. So we're going to do 2 of these together, and then you guys are going to work in your groups and fill in the rest of the blanks. But that magic number is part of the problem. It is made up. On the test, it will be a different magic number, but it is given, okay? This is part of the problem. It's given as 1 to 1 quadrillion. So here's what we do with it. We're going to take 4.4 light years. I'm first going to bring it to miles because light years I can't really picture. So we're going to use this number that I rewrote up here in red. I said 1 light year is 5.88 times 10 to the 12. So what we're going to do is we're going to multiply. I need a fraction, just like we did our hot dog fractions. This fraction has to equal 1. I can't change it. Where do I want to put light years if I want to cancel light years? Top or bottom? You put it on the bottom. So put light years down there, and then I guess we're putting miles up on top. And then we have to put the number. Is it 1 mile and then some light years, or is it 1 light year is some miles? 1 light year is this many miles. That's what's given. 5.88 times 10 to the 12. Okay, if I multiply these things, I'm going to get some enormous number, which will be how many miles it is between us and Alpha Centauri, okay? You can just multiply them and it'll get some enormous number. I can't deal with that enormous number, so we're going to scrunch it down. We're going to make our scale model by scrunching it down, and according to this problem, given in this problem, it said scrunch it down by 1 to 1 quadrillion. So what you do is you multiply by 1 over 1 quadrillion, 10 to the 15. I'm not putting any units. It's not 1 light year or 10 to the 15 miles. It's just a number without any units at all. In fact, it's going to change the game. Is this fraction equal to 1? No. So I'm changing things. I'm not getting the right distance anymore, but that's okay. I'm trying to change the distance because I can't visualize it. So that right there is the one time where we kind of break the rules and you multiply by something that isn't 1. So this thing right here, if I cancel my units, I'm going to cancel the light years. What will the units be when we multiply? It's going to be miles, which is what I want. I want to know how many miles apart in our scale model is Alpha Centauri from us. Yes, Nicole? It's in every problem. It's in this particular problem. It's given right down at the bottom of the page. That's the 1-to-1 quadrillion. 1 over 1 quadrillion. Yeah. And so we're going to see that in every problem that we do right here. Okay, but let's get a number. So we're going to type all that stuff in, and my calculator has shut down to save power. So you could use the E button. I'll just type it out. What is it? Oh, it's 4.4, not 4. I misread the L. Thank you. So we multiply right across the top, divided by 10 to the 15. It's fine to put parentheses around the top and other parentheses around the bottom. You don't need to in this case because there's only one thing in the bottom. So there's no danger here, but it's safe to just put parentheses everywhere. So this is 0.025872. Let's write that here. 0.028572. Did I get that right? 0.02. 0.025872. Oh, 25872. Okay, so let's make sure everybody's getting it. Do we have it?
Did I do something wrong here?
You did 10E15. You should just do 1E15.
Oh, okay, sorry.
If the decimal point is in the wrong spot, so somebody just showed me that on the bottom they had typed 10E15 for the 10 to the 15th. But if you wanted to do that, then what you need to do is think of this as a 1 times 10 to the 15. So it should not be 10e to the 15. It should be 1e to the 15. Lucas. 0.025. Yeah, perfect.
I did that, but I did something.
No, 10 to the 15 is good, but if you use the E button, you don't do 10E15. You would do 1E15. So you got it right. You're fine. Okay.
Oh, I used the EXP one, but I did 10 to 15. EXP, and I gave you the answer.
Maybe type it in again. That seems strange because it feels like that would be one extra zero. Melissa, did we get it? Good. We okay here? We got this number? We're going to do one more, and then we'll answer any questions, okay? I have to take, I'm sorry, I wasn't looking, but I'll take a look at it and we'll make sure we type it in right. Okay, so this is 0.025872 something. What's the something? Miles. So the only unit that we have here is miles, so I'll write it. This is in miles. Okay, now that's not a particularly useful distance to me. I can't visualize it. All right, so I'm imagining the Earth is sitting up here in the corner of the room right on this stool. I'm going to put Alpha Centauri 0.025 miles away. Is that like a few feet? Is it to the other end of the room? Is it downtown Greenfield? I can't tell. I mean, I don't have a sense. At 0.025872 miles. So what do? We got to fix it. We got to convert it into something more useful. All right, you're not going to have to do this for every single problem. But again, in terms of thinking about the test, I would really like you to be able to convert from that number of miles to something more useful. So we're going to do this on a different piece of paper. 0.025872. Did I get that right? Okay, we're going to do our favorite thing for today, multiply by a fraction. What's a unit? Where do I want to put miles if I want to cancel it? Put miles on the bottom, because right now it's up there. What's a unit smaller than miles? Feet. And this is where we put to use the silly numbers that we haven't memorized. 1 mile is how many feet? 5,280. If I want you to use this fact on the test, I will give it to you. I'm not expecting that you all got that number memorized. But if I tell you that there are 5,280 feet in a mile on the test, I'd like you to know how to multiply by the right fraction. Okay, so I'm just going to leave it right there. And I'm just going to take my answer. 0.025872, and multiply by what? 5280. This is going to give me how many feet apart the Earth is from this star in our new multiplying. So it's 136 feet. Can we visualize that? I can visualize that. 136 feet. So the Earth is sitting here on the stool. I don't know how far it is, maybe like 30 feet to the corner of the room. So, you know, maybe we make our way like right above the bookstore, or maybe we're slightly outside the building. I don't know, but I can visualize 136 feet, okay? Okay, so we'll just write that over here. So that was about 136 feet. I didn't see the next number, so it rounds up to 137. Thank you. Yes. This is a fact that 1 mile is equal to, yeah. Okay, so we've got that. Earth in the corner, the Alpha Centauri is 137 feet away. Let's do one more. We're going to do Sirius. So the calculation here looks almost the same. What do we start with? We've got 8.6 light years. What's that? Yeah. And then we're multiplying. Okay, this is a fact about miles and light years, that there's always 5.88 times 10 to the 12th miles per light year. So we're just going to multiply by that. 5.88 times 10 to the 12 miles per light year. And then here's the funny one. Because it's this particular problem and our scrunching factor, our scale factor, was just 1 over 10 to the 15, it always goes on the bottom. I'm just going to highlight them both, that, you know, like this is just part of the pattern of this problem. On your test, it might be a different number, but it's given. Whatever that scale factor is, you just throw it down there in the bottom. Okay, and then we multiply these, and we'll wait for somebody to tell us what they get on the calculator. And if I had to guess, I'd say something like 0.05. What do we have? 0.050568. Sure. So on the calculator, we're doing 8.6 times the 5.88 times 10 to the 12 divided by 10 to the 15. What are the units for this number? Those are miles. Every time you do this, we're going to get miles. Now 0.05 miles, again, I don't have a good sense of what that is. We could go to the other page and play the same game. I'm not going to ask you to do that for any of these problems. I do want to highlight one thing that that Google can do, which some of us might not have been aware of. So if everybody's got what they need from here, we're going to pull up this web page. Okay, so for starters, Google can tell you, for example, 3 plus 4 times 7. Why isn't it writing anything? 3 plus 4 times 7. I mean, like Google has a quite nice calculator that just comes up if you try typing in some arithmetic thing, okay? So that's fine. But here's the part that I think is really nice. The number that we just had here was let's actually do the one that we already know the answer to, 0.025872. Let's come back to here, 0.025872. Did I type that in right? Okay, what were the units for that one? That was miles. I'm going to make this a little bigger so that people in the back can see. That was miles. What did I want to convert that into to make it something useful? Feet. So you can just type in feet. What did we get? 136, yes? Yeah, it makes it so that like the test just, you just type in the, Math 117 first test, it'll just tell you the answers. It's just, so this is kind of cool. And in fact, it's got all kinds of conversion stuff. It just pulls it right up. So anyway, just something to be aware of. All right, so here's what I would like you guys to do. You have 14 minutes. I would like for you to fill in the rest of this table. We've got a bunch of stars that are further and further out. We did not yet do the star that is very close to us, that is the sun. So do that one, but it's the same calculation. But that one's going to be really close to us, and I'm curious, if we're here in the corner on the stool, is the sun in the room? Is it outside the room? Is it basically like right on top of the Earth? So go ahead and start with the sun calculation and work your way through and compare with your neighbors.